Okay, let's conclude this lecture with part 3 on types of transmission lines. So just to recap what we did in the last module, or in the last nugget, we had some simple rules for waves that are propagating on these transmission lines, right? And we're starting out with a simple transmission line, which means that the properties are constant everywhere. The inductance, the capacitance are constant. They don't change with distance. And from this, we figured out that the impedance and the velocity are both constant and can be determined. In particular, the propagation velocity was 1 divided by the square root of LC, and the intrinsic impedance Z0 was the square root of L divided by C. Now, a wave can take any shape we want it to be. Anything that's moving along the transmission line with this propagation velocity and with this impedance ratio is going to work. So it can be a sine wave, it can be a square wave, it can be a little triangle, it can be a single impulse. Whatever it is, though, it's moving up and down the waveguide. We can have a positive and negative going wave that can be different from each other, and they can be independent. One of them could be 0. But for each of those waves, a positive and going wave, we know that the voltage to current ratio must be equal to this intrinsic impedance Z0. One thing I'm going to note is that if I have two waves that are moving in opposite directions, because the currents are flipped with respect to each other, if I add up the total voltage and the total current, that ratio may no longer be the same as Z0. In fact, we're going to see later, it's not. But for each of those two waves, the positive going and the negative going, for each of those waves, the voltage to current ratio must be Z0. All right, now let's talk about different types of transmission lines that exist in the real world. All right, so one simple way to do a transmission line is with two parallel plates. So you can just draw this like this. Imagine these are two plates with a small distance d between them. And this would be a parallel plate transmission line. This is not especially common. Not easy to do this on circuit boards or in integrated circuits, but it's pretty easy to analyze analytically, which is why I'm including it in this discussion. It turns out to be pretty easy to solve the math for how this is going to work as a waveguide. So we're gonna discuss the parallel plate. A much more common transmission line that you have likely encountered would be a coaxial line. A coaxial line will look like this. You have an inner conductor with an outer conductor going around it. So there's a wire inside, and there's conducting material on the outside of this cable as well. And together, you form a transmission line with those two coaxial cables. Right, an example would be BNC cable that you perhaps have used in an earlier lab class. The space in between the two conductors, the inner and outer, can well be filled with a dielectric material. This is likely not air, but it's filled with a dielectric material that probably has a dielectric constant epsilon r associated with it. All right, so there's a couple. Let's go through a couple more. There's one called a microstrip. A microstrip is when you have a trace above a ground plane. So this is called microstrip. This is very common in circuit boards, right? In circuit boards, you'll typically have a dielectric material like this. And on one side, you may have a trace that, as I've drawn it here, but it may be going in and out of the board. And on the other side, it's very common to put a ground plane, right? Or just like a thick square of conductive material. And you might ground that, right? So this is the microstrip, is one conductor down here, one thin conductor on the top, which is basically a wire, and in between is a dielectric constant. This is what your circuit board is made out of, right? And this is called a microstrip. Most traces running on a circuit board look like this microstrip. So this is going to be, fairly important. There's a variation of microstrip called strip line. Strip line will basically involve what looks like 3 conductors, but is really 2. Now I've got a ground plane up here, a ground plane down there. These are tied together, right? These are perhaps, for example, both grounded. And in the middle, I have a wire conductor, right? This is called strip line. This is common in circuit boards where you may have internal layers inside of a circuit board, and you may have two planes, a ground plane on both ends that kind of sandwich that, that single trace that goes in the middle of the circuit board. And so that's a strip line. Another one that's much more common, for example, the power grid would just be two wires, right? This would be a two-wire transmission line. And you can also have what I would call a coplanar strip, which is often mounted on a circuit board, where you have two traces that are sort of parallel to each other. It's similar to two wires, but the wires are not sort of rounded cylinders, but they may be sort of square or rectangular. Right? So this is called a coplanar strip. Right? Now, transmission lines are, you know, something that you would probably start by intentionally designing, right? You go out and you buy a coaxial cable because you want to build a transmission line. You want to carry voltages and currents from A to B. But some of these may also exist parasitically. For example, if I have a third trace over here, you know, I've got a transmission line between these two wires right here, but whether I like it or not, I also have a transmission line between these two and another transmission line between these two, right? So there are transmission lines that are there by design, and there are transmission lines that are sort of there parasitically. And all those have to be taken into account in sort of real systems. Right, so if you take a look at the inside of a coaxial cable, for example, you can see a little more of the structure. This is the innermost part of the coaxial cable is a conductor. It's a thin wire, maybe consists of little strands together, maybe sort of one thick strand. This is very often copper, a you know, pretty good conductor, although getting to be a little bit expensive these days, but that's what a lot of coaxial cables are made out of. And then around that coaxial inner conductor will be sort of some shielding material with the dielectric constant to it, epsilon r. Around that, you'll have an outer conductor, which for mechanical stability reasons is usually not a solid conductor, but it's usually lots, I don't know if you can see it, there's lots of very, very thin strands of copper. They're kind of woven together and wrapped around so that this cable is flexible and you can bend it. It wouldn't if it were solid copper, it would be very difficult to bend. And then around that, you have some sort of like a rubber or plastic shielding just to protect everything that's inside. So this is what we would call a coaxial cable. So the question you might ask is, okay, how do you know what is the inductance and the capacitance of this? If you knew, you know, what was the diameter of the inner conductor, the diameter of the outer conductor, you know, what material is made out of, you could calculate the transmission line properties from this. And so for the different transmission lines that I referred to earlier, here's a nice set of equations of what the inductance and capacitance is for all of them. Now, don't worry, I'm not asking you to memorize this. In fact, I think it would probably be a waste of your time to do so, right? But these are sort of known ways to figure out what the inductance and capacitance is. And the way we solve that, don't worry about that right now, because when we get to electromagnetics, we're basically going to build some of the tools to calculate what these are. For now, just take these at face value, that if I give you a transmission line and I tell you, here is the length of the transmission line and the size of the conductors and their geometry, and I tell you the material that's surrounding them, you can figure out what the inductance and capacitance is as a result if you have a table like this. But again, don't worry about memorizing this. Don't worry about how these are derived. That will come later. All right, so that concludes this lecture on types of transmission lines. In the next lecture, we will be putting this into practice and actually determining how waves propagate on a transmission line. And more importantly, why it's so important and what kind of implications come from the finite delays from one end to the other.